Cái nào nhé. Okay, good morning, guys. Assalamu alaikum. Hope that you guys are doing well. Welcome back to grade 11 Maths by Inspired Teens, where in today's lesson, we are going to be doing analytical geometry. Okay. So, yeah. Okay, so yeah, I hope you guys have been practicing Euclidean and that you guys are coming right. Please, if you have any questions, message me and I shall do my best to help. But yeah, let us continue with analytical geometry, and let us start by going through all of the concepts of analytical geometry. Right? So what is analytical geometry? We don't really care. We just care how to answer it, but we'll read it anyway. Analytical geometry, or coordinate geometry, as we should understand it, because we deal with Cartesian planes, right? X and Y axes and stuff like that. Application of straight line functions in conjunction with Euclidean geometry by using points on a Cartesian plane. How fancy. Okay. Flashback. So this flashback is just basically to discuss the gradient of a the gradient of a horizontal line and the gradient of a vertical line. So a straight line that's parallel to the x-axis, that would be known as a vertical line. Okay, and a straight line that's parallel to the y-axis, that would be known as a horizontal line. Okay, so that's basically what we're here to discuss, right? We're here to discuss the gradients, okay, of a vertical line and a horizontal line. So let's actually get rid of this. Let's do it slightly differently. So I want to draw out a straight line. I don't know if we've done this in any lesson before. Maybe in Euclidean, maybe. So I want to draw out a straight line, and this straight line is parallel to the x-axis, or alternatively, screen is frozen. Okay, I see that. Let me reshare. Thanks for letting me know. Okay, is it fixed now? Okay, perfect. So, yes, this is what we were discussing. We looked at what is the definition of analytical geometry. Okay, but we're talking now about basically the gradient of a vertical line and the gradient of a horizontal line. Okay, so let's just look at this little diagram here in blue that I'm going to draw. I've drawn a line parallel to the x-axis, which is a horizontal line. Now, this horizontal line, it has no slope, right? It's a flat surface, right? If there's a car chilling here, right, provided the car was not faulty, it didn't need its handbrakes up to not move, because it was not, there's no incline on this line. Okay, it's not shifted up or shifted down, right? There's no incline whatsoever. This is a completely flat surface, or a horizontal line. And here we say that the gradient of this line is 0, right? It has no slope whatsoever. It has 0 slope. Okay, then if we increase the slope, perhaps maybe this is, I don't know, 1. Okay, then we can increase the slope even more. I don't know, let's just increase it slightly. Let's just say this is 5. And we can increase it even more. Let's just say this is 10. But then these are not accurate, by the way. I'm just giving arbitrary numbers. Okay. 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 If we increase it even more and we go vertically upwards. Okay, so we went from completely flat, no slope whatsoever, okay, to a slightly bigger slope, then a bigger slope, then a bigger slope, okay, until we get to somewhere now where we are pointing directly up, vertically upwards. Okay, in that situation, right, what would be the gradient? Would it be 12? Would it be 15? Would it be 20? Would it be 17? Would it be 20 million? Would it be 17 million? Okay, we don't know. Okay, and that's why we call this undefined. So the gradient of this vertical line is undefined. Okay, so I hope that makes sense, right? I hope that you can see how the logic behind what I just explained, so help you remember it. Okay, so the flat surface, which is a line that's going to be parallel to your x-axis has no slope, has no gradient, right? If you picture a car on a flat surface, it shouldn't move, right? However, if I'm going to put a car here, well, let's just say, I don't know, a skateboard. Okay, that's a bit different. The skateboard is going to move down. Okay, yeah, on any of the other slopes as well, right? Except on that one. That's when we say, okay, in this case, the horizontal line that has no gradient, zero, a gradient of zero. Okay, and then as we increasing directly up, it's undefined. We're unable to determine what type of gradient that is. Okay, so yes, that's what this is telling us. Vertical line, no gradient, m is equal to 0. That's what m is, gradient. Straight line, parallel to the y-axis, gradient is undefined, and you should always remember that. Okay, in fact, when we do functions, we discuss the equation of a vertical line and the equation of a horizontal line, and I'm actually going to do that now, here, while we have some space. So, equation of a horizontal line and equation of a vertical line, right? That's fine. Okay, so here's my vertical line. Okay, and I'm not going to take too much time spending too much. I'm not going to spend too much time here. Let's just say it touches there at y at 2. Okay, so what you should know is every vertical line has an equation in the form x, not y. So I know it's a straight line, and normally straight lines, if I ask you what's the straight line formula, you'll say y is equal to mx plus c. Okay, except for vertical lines, they have an equation in the form x is equal to whatever the x value is on that line, because the x value is constant, right, throughout this line. Not 3, 2. The x value is constant, right, throughout this line. It doesn't change. It's a vertical line. That's also another thing you need to note. X values remain constant on a vertical line. This is very important, and many people forget it. Okay, so that's the equation of a vertical line, right? We will discuss this again when we get to functions, but I just want to quickly mention it to you here. Always. So whatever the x value is on that vertical line, its equation will be x is equal to that x value. Let's talk about the horizontal line, all right? So let's throw in this horizontal line and its value here. So the first thing to note is that the y value on this horizontal line remains constant. Wherever you are on this line, you're going to have the same y value, whether you're here, wherever, whatever the x value is, the y value remains the same. So let's just say this is -1. The equation of a horizontal line takes the form y is equal to -1. Okay, so that's just a quick way just to remember it. Vertical line, x is equal to whatever the x value is. Horizontal line, y is equal to whatever the y value is. We'll get into the y is equal to mx plus c once we do functions. Okay, but that's important to note. The equations of straight lines, not the equation of straight lines, the equations of vertical and horizontal straight lines. Okay, then we move on. Straight line equation, y is equal to mx plus c. That's amazing. We love that. Okay, where m is what? M is gradient. Okay, and what is c? So we should know m is gradient. And what is c? C is actually the y-intercept. Okay, c is the y-intercept. Okay, so always keep that in mind, right? So sometimes when you're given an equation in the form y is equal to mx plus c, perhaps y is equal to 5x plus 3. In this case, you don't need to work out the y-intercept because you already have it from the equation. It's 3. All right, so just keep that in mind, and that's why that's important. Let's have a look now at the gradient formula. Gradient formula, m is equal to delta y over delta x, change in y over change in x, y2 minus y1 over x2 minus x1. So this should just be revision for you, right? You've done this formula probably since, I don't know, like at least grade 10, definitely at least grade 10, maybe even like way before that, right? But this is the gradient formula, y2 minus y1 over x2 minus x1, and hopefully we can get to do an example today as well. Then we look at parallel gradients and perpendicular gradients. So there's a relationship between the gradients of the parallel lines and the gradients of perpendicular lines. That's important to note. Okay, so firstly, simple, gradient of parallel lines equal. Okay, gradient of perpendicular lines, when you multiply them, you should get -1. So these are what parallel lines look like. Lines that are traveling in the same direction but will never touch each other. Okay, that just makes sense. They adjacent to one another, traveling in the exact same direction, It just makes sense that they have the same slope, right? The angle at which they are is the same, right? How they orientated, right, has to be the same, because then if they're not, then they wouldn't be parallel lines. Okay, so the gradient of parallel lines equal. Okay, then we have perpendicular gradients. So the gradient, we're talking about the gradient of perpendicular lines. What are two perpendicular lines? Two perpendicular lines are lines that are at 90 degrees to one another, like these two lines. Okay, the one is vertical, one is horizontal. Now the relationship between the gradient, doesn't matter which one is M1, doesn't matter which one is M2, really doesn't. When you multiply their gradients, you should get -1. That's their relationship. Okay, these are important. These will probably this is definitely going to be in your exam. Some concept of testing this is always there, always, right? Most things in analytical are always there. But like, for example, distance might not be there, but this, you know, for sure is guaranteed going to be there. You have to understand this. It's very important. Okay, you need not forget it as well. This is extremely important. Understanding that the gradients are parallel. The gradients of parallel lines are equal, and the gradients of perpendicular lines, their product is -1. Then we talk about distance formula. Distance is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. So these are given, right? Distance is given, gradient is given, straight line equation is given. Okay, obviously this is not given. All right. Let's talk about the concept collinear. Okay. So we'll read the sentence at the bottom. It basically says collinear points A, B, D, and C are on the same line. So when we have 3 points or 2 points, any 2 points on the same straight line, we call these points collinear points. Very important. When we have any 2 points on the same straight line, we call them collinear. Collinear meaning together on a linear graph, on a straight line, together on a straight line. So collinear. Okay, so A, B, and C, for example, A, B, and C are all collinear to one another. So in this case, all right, let's have a look at this. This is key and important, of course. The gradient of AB is equal to the gradient of BC. That's definitely true. The gradient of AB from A to B is equal to the gradient of BC. That has to be true because it's the same line. A to B and B to C, they form part of the same line. So they have to have the same gradient. Otherwise, if they didn't, then B to C would look skewed like this or something like that. Right? So that's definitely true. The gradient of AB is equal to the gradient of BC. But another thing that's also true is that the distance from A to B, this is not like, so like, it's whatever, like you might use it, might not. It's not so important, but nevertheless, the distance AB plus the distance BC is equal to AC. That is like obvious, right? Distance AB, they're not equal. The distance AB and the distance BC, when you add those two together, you'll get the distance of the whole thing, AC. Okay, but that's just, again, telling you that these distances, when you add them up, they give you the big distance because it's a straight line, right? Because it's all in a straight line. Okay, so that's collinear. Midpoint formula. So midpoint does exactly what it says. It finds the middle point of two coordinates. So if you want to get the midpoints of X and Y, two different coordinates, right? Midpoint. You want to, you will say, use the formula x2 plus x1 over 2. That's to get the X midpoint. Or midpoint X rather. And then to get the Y midpoint, you'd say y2 plus y1 over 2. That's how you find the X and the Y coordinates of the midpoint. Okay, so converting, okay, before we'll discuss midpoint theorem in a bit. Let's look at this, converting gradient into angle of inclination. Gradient is equal to delta y, blah, 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 blah. Okay, this is a very formal way of introducing it. Let's do it here, right? You can go through those notes. They do make sense, but I just want to go through it here because it's a bit easier. Okay, so now you're going to learn that there is a relationship. You probably already know this again from grade 10. Maybe not, I don't exactly remember. But yeah, you're going to learn that there's a relationship between gradient and the angle, not any angle, okay, more specifically, and they mention it there, right? And I'll mention it here as well. Let's create some space. There's no the relationship between gradient and angle. Okay. When we talk about angle, okay, theta, I'm going to call it theta. Theta is always the angle of inclination. With the x-axis, okay, from the right. Theta, the angle that we work with, okay, is always the angle of inclination. So when we talk about this, whether we're getting the angle or whether we're getting the gradient, the theta that we are working with is always the angle of inclination with the x-axis from the right-hand side. Okay, so let's just see. Okay, when the so this is the top thing, or when the angle is known versus when the gradient is known. So when we have the angle, what angle are we talking about? When we say angle known, what angle is known? This angle theta, which is described as this. It's the angle of inclination with the x-axis from the right, which is depicted here in this little diagram. This here, 63.43, is the angle of inclination of this nice little cute straight line that we've drawn on the x-axis from the right. Okay, so it sounds maybe complicated, but there's it simple, easy, makes sense, right? It's the angle of inclination with the x-axis from the right. That's exactly what we're dealing with here. That is the theta that we talk about. That is the theta that we talk about. So now, since we have the angle of inclination of this line, what is this whole concept that we're discussing? If we have the angle of inclination of a specific line, a straight line, we can get its gradient, basically. If we have the angle of inclination of a specific straight line, we can get the gradient of that straight line by utilizing this. Tangent theta is equal to m. So if the angle is known, you just have to say tangent theta. Tangent theta is equal to m. And I will say tangent, what is my theta? 63,43. Okay, so you put that in your calculator. This is not shift tan. This is just tangent, 63.43. And I get 1.99956. I generally want to round off to 2 decimal places. As soon as I round this off to 2 decimal places, I get an answer of 2. So therefore, the gradient of this line is equal to 2. Okay, so when the angle is known, you can get the gradient by using tangent, sub in that angle, it's going to give you the gradient. Okay, what about if the gradient is known? Okay, so we have again the straight line, right? And here the gradient is given, m is equal to 5, right? Sometimes it might be given in the form, they might not explicitly say the gradient of this line is this, but they might give the straight line equation. Y is equal to 5x plus 3. Again, the gradient is known because remember, this part of the equation is gradient. 5. The m before the x is gradient. Okay, so what happens when gradient is known? So let us maybe do this, move it down. Okay, so what happens when gradient is given or gradient is known and you want the angle of inclination? And this angle is wanted. Okay, so I hope you're understanding, right? From gradient, we go to angle of inclination. From angle of inclination, we can go to gradient. Okay, what happens when the gradient is known? I follow this formula. Shift tan, or you could even write it out as tangent theta equals gradient. And then because you know gradient, to sub it in there, you have to say shift tan. Then you say shift tan. The gradient here is 5. And that's going to give me theta. And I can get theta. Therefore, theta is equal to, so now you take out your calculator and you say shift tan 5. shift tan 5 gives you an angle of 78.69 degrees. And that's your angle. So your final angle here is 78.69 degrees. Okay, it's the angle of inclination. So if you wanted this angle here, and you just say 180 minus that angle, you'll get it. Okay, but this formula only gives you angle of inclination. Now, that was a positive gradient. What happens when we work with a negative gradient? Okay, so when we work with a negative gradient, here I'm going to say tangent theta equals gradient, or you can directly write this also, it's fine. Then I'm going to say, therefore, shift tangent gradient is going to give me theta. So when I solve for theta, I'm going to say, sorry, I should say shift tan negative 1/2. So I have to say negative 1/2. That's my gradient, right? So in my calculator, if I put shift tan negative 1/2, I get a negative answer, negative 26.57 degrees. Okay, so of course I cannot get an answer with a negative angle. So what do I do in this case? Really simple. Basically, whenever you're dealing with negative gradients, once you calculate your theta using shift tan, okay, what you're going to then do is just add 180 to make it positive. So now I take it in my calculator directly and put add 180, and I finally get an answer for theta. This is, remember, why do we do this? Because we're working with the angle of inclination. 153.43. So this angle of inclination from the right with the x-axis, this angle is 153.43. Okay, so that's angle of inclination. Just by the way, this negative angle that you got was actually this angle, yeah. But yeah. Okay, so that's how we use, what's this? This is how we use tangent and gradient, or rather angle and gradient, angle of inclination and gradient to solve for each other, right? Whichever other one. Okay, so yeah, you can go through this formal blah, 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 yeah, if you like. But yeah, let's move on to this. Don't you take out the negative. What do you mean by reference angle? When you say reference angle, do you look there? There is possibly another way to approach it. So you might be right. But what do you mean by reference angle? Like what angle are you talking about exactly when you say reference angle? But this also works, right? Just adding 180 to get your positive answer, that works 100% as well. Okay, gives you the angle of inclination. Okay, I'll wait for you to respond and then I can address that again. Okay, let's look at this, right? Finding an angle that is not related, not in relation to a horizontal plane. Construct a horizontal plane, blah, 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 blah. Okay, before we get to constructing that, let's just have a look at this, right? That's not there. Okay, let's see if I can cheat quickly. Okay, no, we won't cheat. We'll do the example. But cheat a little bit. Excuse me. Okay, let's have a look at this diagram, this little diagram. Okay, we have an x-axis, we have a y-axis, and we have a nice little triangle. Okay, so now the angle that they want you to solve for is this theta in the corner, right? This little theta in the corner, that is the angle that they want you to solve for. Okay, so the thing is, how in the blue moon do we solve for that angle? Because we only learned angle of inclination, which is there's two lines that cross the x-axis, namely this guy and this guy. Okay, so we can get, if we know their gradients, we can get this angle. Right, this is one thing you also need to know. First step, right? The first step in solving these weird angle questions is to understand the angles that you can solve first. okay, is to get the angles that you can solve for. Understand, that's a brilliant first step in solving for these weird angles. Write down a little arrow to show the gradients, the angles that you can solve. So basically, any angle of inclination that crosses the x-axis, put a thing there and say, okay, listen, I can, although I know that I need to solve for this guy, okay, I don't know how the heck to get there yet, but let me just take down which angles can I obviously solve for. So I can solve for this guy if I have the gradient of that line, and I can solve for that guy if I have the gradient of that line. Okay, so that's the first thing, right? Now, that's the first thing. Then that's step number one. Just identify the angles that you can solve using gradient, which is these two, right? They cross the axis. Number one. Number two, okay, see how you can relate those angles with the angle you need to solve. So again, I'm going to call this guy I'll find beta. I'm going to call this beta and alpha. It doesn't matter. I'm going to call this guy alpha and this guy beta. Okay. Okay, I'll get back to you in a second. Okay. So I'm going to call that alpha and beta. Now I have to figure out a way, how can I relate these two angles to theta? And the answer, majority of the time, is simple and is triangle. Majority of the time, not always, okay, but a lot of the time. It's to use a triangle to relate these three angles. Okay, so how am I going to use the angle, this triangle, to relate these three angles? Remember that this angle here inside the triangle, sorry, is also equal to beta. Why? Because of vertically opposite angles, right? This guy is equal to this guy. And then the rule that every single person in the whole universe, not true, okay, exaggeration, but it's needed. The rule that everyone forgets is exterior angle of a triangle. Exterior angle of a triangle. So they can give us other shapes. What do you mean by other shapes? Generally, they give triangles or quadrilaterals. That's what they stick to. Triangles or quadrilaterals. Okay. So in this specific case, we can use exterior angle of a triangle. Okay. Where we can say that theta is supposed to be equal to, we can say that alpha is supposed to be equal to theta plus beta. Okay, I haven't solved for anything, but I'm busy problem solving. That's what I'm trying to do here, right? I'm trying to figure out how can I calculate this angle. Okay, so I said vertically opposite angles, angle beta is equal to that angle beta, vertically opposite angles. And then I need to identify that alpha is the exterior angle of a triangle, and it's equal to the sum of the opposite two interior angles. So that's why I'm saying that alpha is equal to theta plus beta. Okay, I hope that makes sense. Okay, so now I've found a way to solve it. So the first step is I'm going to get the gradient of KL. This is going to be equal to y2 minus y1. So 6 minus, y2. So I'm working with K and L. So my y2 is going to be, I'm going to do 2 minus 3. 2 minus 3. And I'm going to do 6 minus 2 for the x. Okay, and yeah, I get an answer of 5/8. What a not nice number. Okay, I get an answer of 5/8. Okay, so that's the gradient of what? The gradient of KL done. Let's do the gradient of JL. 3 minus 3 divided by -4 minus 2. And I get an answer of -3. Cheating a little bit, but it's fine. Okay, so I know the gradient of this line is equal to 5/8. And I know the gradient of this line is equal to -3. Okay, so now when I have the gradients, I can solve for the angles, right? So let's solve for beta. So beta, whenever you have the gradient, okay, what do you say, right? Remember the formula is, I'm going to write it in terms of beta, tangent shift gradient gives you the angle of inclination, okay? So I'm going to say that beta is going to be calculated by saying shift tan, what's my gradient? 5/8, right? It's the gradient of that straight line. Right, it's going to give me the gradient of the straight line. Oh, sorry, I have the gradient of the straight line. Okay, I calculated it using gradient formula because I have two coordinates. It's going to give me the angle of inclination of that straight line, okay, which is really what I want. When I shift tan 5/8, for beta, I get an answer of 32,01. Okay, so beta is 32,01. Okay, then what do? I do the exact same thing for JL. So I used my same formula, shift tan gradient of that line is going to give me alpha. Okay, and alpha can be solved by saying shift tan, the gradient of that line is -3. Okay, so I'm going to get a negative answer, shift tan -3. So what do I do when I get a negative answer? Or in general with negative gradients, I just always add 180 degrees afterwards. And when I add 180 degrees, for alpha, I get a solved angle as 108,43. (108,43 degrees). Okay, so I've solved for those two angles. Okay, let's get rid of. Okay, it's fine. Alpha is equal to 108,43. Beta. Beta is equal to 32,01. So this guy is also equal to 32,01. Okay, so now remember we said that theta, alpha is equal to theta plus beta. Okay, so that's exactly what we're going to do now. We're going to sub it in. Alpha is, we solved it as 108,43. Theta is what we want to solve for, plus 32,01. You take 32,01 to the other side to solve for it. You get theta's answer as 76,42. Okay, so that's how you solve it. Theta is equal to, so any questions? Okay, don't you take the negative out when you put in your calculator, which gives you a ref angle. Ref angle is the answer you get after putting shift tan M. Then you subtract 180 from your ref angle. If you do that, if you take out the negative in your calculator, it's going to give you positive. It's going to give you a positive answer. And when you subtract 180, you're going to get a negative answer. So you shouldn't do that. You should put in the negative answer and then add 180 outside of the angle. That gives you a positive angle of inclination. Okay, so I hope this makes sense, right? It maybe looks a bit complicated, but that's just because I calculated all the gradients and blah, blah, blah. Let's get rid of all these extra shenanigans all over the show, right? But this is the basic concept. Okay, basic concept is you need to find the angles that you can find using angles of inclination with different gradients, number one. Number two is you need to see how you can relate those angles to the angle that you actually want to solve. And a lot of the times, trust me, you will see that it's, oh, I can use exterior angle of a triangle. Okay, you actually don't have to give reasons for this part, by the way. Like you don't have to say vertically opposite angles. Like you can just solve for that angle of inclination, solve for that angle of inclination, and then subtract them from each other to give you theta. A lot of the times teachers teach, calculate the two gradients and say bigger minus smaller. Okay, which is fine in most questions, but I'm just teaching you the logic behind it in case it's not the exterior angle of a triangle. What happens if it's something else? Then how are you going to use your brain to solve for it? I don't know, but now hopefully you'll be able to do that because you understand the logic behind it, right? Trying to relate the angles that you can solve to the angle that they want you to solve, because there's no magic formula to get us theta, right? There's no single formula that we can use, shift tan, shift sine, whatever, to get us theta. We're using our knowledge of Euclidean, not Euclidean, analytical geometry, where we learned in analytical geometry how to work with tangent and gradient, right? Gradient and angle of inclination, how to interchange between the two. So we're using that information to solve for theta, okay, using other properties of this specific triangle. Right, let's look at this diagram. Now, here's another way which you can think about it. So we have the exact same diagram, x-axis, y-axis. However, now what they've done is they've fitted in this horizontal line. So where theta is, this is, I don't really prefer this, but if this makes more sense to you, right, you draw in a horizontal line where theta is. Okay, because now that you have a horizontal line, remember that this horizontal line of yours is parallel to the x-axis, right? So since it's parallel to the x-axis, it behaves just like the x-axis, right? And then what you do is, so remember, this is the angle of inclination. This is the angle of inclination of the of that line with, what you call it? This is the angle of inclination of this line with the x-axis, and it's equal to this angle here, right? Remember, this is the F, it's the corresponding angles. These two angles are equal to each other, right? So getting this angle is the same as getting this angle, but you want to work with this. Since you drew your new horizontal line in, how do you get beta? It's angle of inclination, and you have the gradient of this line, okay? Then you can get alpha as well. So alpha would be slightly different because remember, you're going to have to say 180 minus your answer because angle of inclination is going to give you this one. And then you would want this one, right? You say 180 minus, you would get this one here. And then this one would be equal to that one, corresponding angles, right? That's basically the logic behind it. Okay, so you can think of it like this as well. I don't know if that makes sense. I hope that it does. So yeah. Okay. So please keep that in mind. Right, let's discuss the second last thing. If there's any questions, let me know. Right, but analytical generally is not too bad. You want to try and get like a really good marks for analytical, right? Okay, midpoint theorem, let us discuss it. It says, if two midpoints on adjacent sides of a triangle are joined by a straight line, the line will be parallel to and half the distance of the third side of the triangle. That makes no sense until we look at a diagram. So let's have a look at this diagram. So we have initially one triangle and, okay, one big triangle, actually, sorry. And what happens is, we find, okay, let's erase this. Okay, what happens is we find the midpoint. So we have two triangles. We find the midpoint of this AC and AB. So here we can find midpoint. So let's just say the midpoint of this is somewhere there, and the midpoint of this is somewhere there. Okay, I'll probably change it up a bit or just go back. Okay, so we find the midpoint of the adjacent sides, AB and AC. We find its midpoint, and we connect its midpoint. Just like this. We find the midpoint of AD and we find the midpoint of AC and we connect their midpoints. When we connect the midpoints of two adjacent sides of a triangle, this is what the midpoint theorem is. Because we've connected the midpoints, it has to mean that that line that connected the midpoints is parallel to the third side of the triangle. This is definitely true. Okay, so these two are parallel. Okay, why? Because we connected the midpoints, right? Because if we had to connect it to any other place, it wouldn't be parallel, right? Connect it there or connect it there, right? It's not parallel, but when we connect it perfectly to the midpoint, it has to be parallel, right? So yeah, even if you, okay, you guys will learn proportionality theorem next. Yeah, but it's fine. Okay, so just keep that in mind. That's important to keep in mind, right? We're connecting the midpoint. So that's why logically it makes sense that this is parallel to that. Okay, so just keep that in mind. So that's that. Now, another thing is this here, the third side is exactly double of the side that joins the midpoints. So the midpoint is half the size of the third side. So for example, if the line that joins the midpoints is half D, then the bottom third side of the triangle is double of that, which is D. Okay, I hope that makes sense again. So let's just look at the two different versions of it that we need to understand. Okay. So there's two actually, there's a converse and there's a regular way, right? As there is with so many things. So if it is given, right, that D is the midpoint of AB and E is the midpoint of AC. Okay, it can be given in a sense where they write it, or it can be given in sense of it's given in the diagram. So they tell you like this. This is equal to this. Okay, so D is the midpoint of AB. That's done. And then they tell you that E is the midpoint of AC. So they're saying that AE is equal to EC. Okay, so AD equal to DB and AE equal to EC. Please keep in mind, AB does not necessarily have to equal to AC. They could be different in length. The main thing is the midpoints. Okay, so that's what, according to this given statement, D is the midpoint of AB and E is the midpoint of AC. That's what I mean in the diagram. Okay, so if it is given, people, if it is given that these, if both midpoints are given essentially, and the line is drawn between the midpoints. Okay, so if it's given that D is the midpoint of AB and E is the midpoint of AC, what you can deduce from that is, what you can solve for, you can say, therefore, DE is parallel to BC. So that's the first thing. DE is parallel to BC. And the second thing is DE is half of BC. DE is half of BC. Okay, so two things that you can use from midpoint theorem, right? So if it is given to you that D is the midpoint of AB and E is the midpoint of AC, you can say, therefore, DE is parallel to BC. Your reason for that would be midpoint theorem. Or you can also say, therefore, BC is twice that of DE. What's your reason for that? Midpoint theorem. Okay, so that's the point of using it, and that's how you use it, right? I hope that makes sense. Okay, and your reason, as you can see, for both of these, you could use, if you want to use the parallel one, or it depends on the question, obviously, then your reason for both of these would be midpoint theorem. However, if it is given that D is the midpoint of AB and DE is parallel to BC, so let's do this. Yeah, that's small. I'll enlarge it and then reduce it again just now. Okay, so we're working with the same one, right? Okay. Basically, it says if D is the midpoint of AB and DE is parallel to BC, so if only this is given, if only this is given, meaning they give you that on one side of the triangle, the midpoint is drawn, indicated. Okay, we don't know if E is the midpoint. It's not given. They don't tell us E. They don't tell us specifically E is the midpoint of AC. They only tell us that D is the midpoint of AB, but they also tell us that DE is parallel to BC. So that's what's given. One side midpoint and parallel lines. That's basically it, right? So if D is the midpoint of AB and DE is parallel to BC, then you can conclude that AE is equal to EC. So now you can conclude that, okay, therefore that means E is also the midpoint of AC, and your reason for that would be the converse midpoint theorem. So converse midpoint theorem, you'd use if both midpoints are not given, okay? So if one midpoint is given and the parallel lines are given, you could say that, you could basically say that the line that it joins, DE, it joins at E, E is definitely then the midpoint of AC. Again, that is what we call the converse tan chord, not converse tan chord theorem, sorry, converse midpoint theorem. Okay, so yeah, hope that makes sense. Yeah, that's basically this thing. Okay, so let's move on to one more thing before we do move on to the question, which I'd like to start the question. We maybe will, maybe won't. We'll actually start the question and then you guys can either continue it, but we'll finish it up next week as well as continue it next week's topic. Okay, so let's have a look at this, right? Just one concept I want you to understand when it comes to midpoint, just a little bit of a calculation thing. So midpoint generally is really easy, right? What happens if I say, calculate the midpoint of these two, calculate the midpoint of AB. Right, what's the midpoint of AB? You're going to use your midpoint formula. So x1 plus x2 over 2, and then y1 plus y2 over 2. So here you're going to get -3 plus 2 over 2 and -2 plus 4 over 2. So here you're going to get -1 over 2. And yeah, you're going to get 1. So that's midpoint, right? So that's basically how you can calculate midpoint AB. It's quite easy. Okay. So what happens in this case, right? So this is a very specific case. I just want you to understand it properly and do an example in case it comes out in the future, right? Look at this, right? Midpoint specifically. And this is also important because you can use it in the properties of parallelograms, okay, which we'll go through actually just now. Okay, so now let's have a look at this, right? We have AC and B. So AB is a line, and in the center of it is C. How do we know it's the center? Because it shows us that A to C is equal to C to B. Since A to C is equal to C to B, okay, if A to C is equal to C to B, then definitely C is the midpoint of AB. Okay, so that's the thing to note. We definitely know that C is the midpoint. However, what is known? Normally, either side, A and B, right, is known. What is unknown is the midpoint itself. However, in this case, one of the points are known, and the midpoint is known, and the other point is not known. Okay, so how do we work from there? Just give me 1 second. And I'll tell you a very interesting thing, actually, about analytical geometry. Okay, it is impossible, it is rather not possible, okay, to solve for 2 coordinates at once. Okay, I'll briefly discuss this now, and when we do questions, maybe more in depth. It's not possible to solve for an x and a y at once, like just in one step or with one calculation. Okay, except using midpoint. The only way we can solve for an x and a y at the same time in one calculation is using midpoint theorem. Okay, so this is actually quite important, because when you get to questions where they want you to solve for a whole coordinate, the midpoint thing must come into mind. So how do you solve this? It's actually quite simple. Okay, what you're going to do is you're going to set up this exact same formula, okay, and just fill in what you know. So we're going to calculate the midpoint of AB, of course, right? That's our objective. Let's do this so we have more space. We want to calculate the midpoint of AB, of course, and this is going to be equal to, firstly, we can just write it as x1 plus x2 over 2 and y1 plus y2 over 2. Okay, so x1 we'll consider as -5 plus, what about x2? X2 is unknown. Okay, so that's why I put it as x and y, right? They might not even give you that. Okay, they might say calculate the coordinates of B. Okay, let's write that actually. So that okay, yeah, hopefully you guys will understand calculate B. I don't need to put the word coordinate in because I'm lazy. Okay, so B's coordinate, we consider it as x divided by 2. Okay, but now before we move on, right, remember in this formula, okay, when you say x1 plus x2 over 2, that answer gives you the x midpoint. Okay, and then when you say y1 plus y2 over 2, that answer gives you the y midpoint. So that's what I'm going to do. I'm going to sub it in. I'm going to equate it. Why am I doing this? Because I actually have the midpoint coordinate. So the x midpoint is 6. Then for the y's, I would say, my first y, I work with the same one, 1 plus b's, this should be b's y's coordinate, which I don't know. So I'm going to call it y, divided by 2. And this should give me 2, because that's the y midpoint. Okay, so now I've set up basically two equations, so I can solve for them. So I can take the 2 over as multiplication. Negative 5 plus x is equal to 12. Multiply that, those two together. And then 1 plus y is equal to 4. Okay, and then I can solve it. How so? Taking that over, I get x is equal to 12 plus 5 when it goes to the other side, 17. And y is equal to 4 minus 1, which is 3. So therefore, B's coordinates are 17 and 3. Is that correct? Kind of doesn't look correct. Yeah, it does, because that's negative 5. And then 1, 2, 3. That makes sense. It's a very, very inclined line, actually. Okay, so I hope that makes sense. All right, setting up an equation, okay, to solve for an unknown third coordinate instead of like the actual midpoint coordinate. This is when you do have the midpoint coordinate. Okay, and you'll see we're going to come back to this concept when we do our question and when we discuss parallelogram, right? I'm sure if you've done some questions, you would have come across a question that asks you to prove something's a parallelogram or find the coordinates. If A, B, C, they'll normally give you a triangle and triangle is ABC. Then they'll put in an imaginary fourth coordinate and say, if A, B, C, D is a parallelogram, calculate the coordinates of D. And you're like, what in the world do I do? Okay, that's where we'll come back to this. This concept here. You could, it's one of the ways to solve for that is using this. Okay, so yeah, that's midpoint concept. But yeah. Okay. Okay, so that's all the time we have for now. So we don't have time to do a question. Next week, we'll finish the question. However, before we do leave, I just want to leave with some other notes that I left here, some of my old notes that I put in here, which are very important for analytical geometry, right? It's the basic properties of quadrilaterals. These are very, 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 very important. You have to know them because they love to test these in the exam. Okay, especially when you guys get to grade 12 in your final examination, right? You'll know all the hectic things like, I don't know, whatever hectic things there in analytical geometry, nothing's really too hectic, but you know all the hard examples, but then you might not get a question just because you don't know that, oh, actually in a rectangle or in a rhombus, the diagonals bisect at 90, or in a square, the diagonals bisect at 90. You didn't know that property of a basic quadrilateral, which you learned like in grade 8, okay? But it's important, right? So that's why I put them down. So quadrilaterals, which are four-sided shape, quad, okay? The parallelogram, so go through them. I'll just like brief through them for now. Parallelogram, opposite sides are parallel, opposite sides are equal. So then there's some hints here, opposite gradients are equal, right? If they parallel lines, gradient equal, opposite sides are equal, distance formula. Diagonals bisect each other. Midpoints are equal. This is coming back to that midpoint thing. Okay, diagonals bisect each other, meaning they cut each other into two equal halves. Okay, this diagonal cuts here, cuts there. This diagonal cuts here, cuts there. Okay, so yeah, but diagonals, so basically their midpoint is both E. They both have the same midpoint, which is E, with the same coordinates once we put it into a Cartesian plane. Okay, and then one pair of opposite sides are both parallel and equal, opposite angles are equal. So if you prove any of these, you've proven it's a parallelogram, by the way. This is just another thing maybe for Euclidean perhaps. Okay, rectangle, all properties of a parallelogram, a palm is short for a parallelogram, except a rectangle has all 90-degree angles. So it's exactly like a parallelogram, except it has 90-degree angles. And then once you prove something to be a parallelogram, you just need to prove. So this maybe is like more grade 8 proving that it's a parallelogram, but it's a possibility that they might ask it here or in Euclidean, right? You just need to prove, once you prove that it's a parallelogram, then you just need to prove that one angle is 90 and then you're done, right? Diagonals are equal in length. So in this case, what's different is here the diagonals bisect each other, but the diagonals are not equal, right? This diagonal's length is different to this diagonal's length. You can see that one is longer, right? So therefore, they bisect each other, but they're not equal in length. But when you look at a rectangle, in a rectangle, the diagonals are actually equal. So when they bisect each other, all four of these halves are equal to one another. Okay, so that's another interesting property of a rhombus. So you need to know all of these, right? And then obviously opposite sides are parallel, opposite sides are equal, and then corner 90 degrees. Let's look at this rhombus. All sides are equal. In a rhombus, all sides are equal. Number two, opposite sides are parallel. They're also parallel, all right? Okay. Diagonals bisect at 90 degrees. That's an important one. They love asking these things. Diagonals bisect. This could also be in Euclidean geometry, by the way. This is not just for analytical geometry. In like one of the finals papers, right, you'll see a 2018 metric paper, 2019 metric paper. I think they used a rhombus in 2018 or 2019. I think it was 2018. Yeah, they used a rhombus. 2018 and 2019, they used a rhombus. And yeah, you have to know the properties of a rhombus. In this was Euclidean, it is actually trigonometry. So it is the application of trigonometry, which you guys will do next year. Or you guys have done it actually. Application of trigonometry. They asked a question with regards to a rhombus. And you have to know that the diagonals bisect at 90. You have to know that they equal to one another, all of that, right? And again, you understand maybe the hard concept of how to apply trigonometry, and you know all the sine rule and cos rule and area rule, but if you don't know the basic properties of a shape, you wouldn't be able to solve that question. So that's why these are important, right? So this is an important one of rhombus. Diagonals bisect at 90. Then diagonals bisect the angle. So here the diagonals are not equal, right? So yeah, but the diagonals in this one also bisect the angle. So where the diagonal touches the corner, if the whole thing is 60, it bisects into 30, right? So that's another weird important property to note. Okay, which you probably have forgotten. Let's look at a square, show that all sides to be equal, so all sides are equal, and one angle is equal to 90. Diagonals of a square also bisect at 90, and diagonals are equal in length, just like a rectangle, and the diagonals also bisect the angle. So we have 90, it separates into 45, 45. Okay, and a kite, adjacent sides are equal, the sides which are next to one another. That's what adjacent means. Diagonals also meet at 90, and the vertical diagonal bisects the horizontal diagonal. So this diagonal here, it bisects, means it cuts in half this diagonal. That's what that means. Okay, so that's a kite. Okay, the kite is the only non-parallelogram in these notes. And I made like a little summary in like informally, we call it the straight shapes. Okay, this is, never mind. The straight shapes and the skew shapes. Okay, straight meaning they're not skew. Okay. And then long shapes and short shapes. So straight shapes, these have common properties. Okay, and the skew shapes have common properties. But the long shapes also have common properties, and the short shapes also have common properties. Let's look at some, right? So the straight shapes, what's common between them? You can see, oh, their diagonals are equal. That's common, right? Also, 90 degrees, right? Those are the common things, right? But let's look what's common between the skew shapes. The skew shapes, diagonals are not equal, and that's about it, I guess. Diagonals are not equal. So obviously opposite angle, oh yeah, I don't know if it's in notes. Opposite angles are equal. Yeah. Okay. Then what else is common? It's just a way for you to memorize it, right? You go through it on your own, and it's just a quick way to like sort of memorize it. What's common between the long shape? So this is the parallelogram and the rectangle. What's common is they both don't bisect at 90 degrees. The diagonals don't bisect at 90 degrees, and the diagonals do not bisect the corner angles as well. However, with the short shapes, both of them, the diagonals bisect at 90, and the diagonals bisect the corner angles. Okay, so just a little table that to help you remember it. Okay, but that's us done. All right, we've covered all the concepts for analytical geometry. And then next week we shall finish up this question and hopefully start the next topic, which is functions. But yeah, anyways, I'll leave it open for the next like 2 minutes to see if anyone has any questions. Yeah, how was your paper one yesterday, by the way? How did it go? But yeah, while we ask how the paper went, yeah, so that's the plan for next week. Thank you guys so much for joining, by the way, for those of you who need to leave or are leaving. Hope that you guys learned, and hopefully analytical geometry and angles and all of that made sense. And then when we do a question, hopefully it makes more sense. But yeah, please, the properties of quadrilateral is very important. Make sure to go through it. So yeah. Okay, it wasn't so bad. Okay, that's good. Hopefully you do well enough or get the mark you're aiming for. Paper 2 is on Monday. Yeah, good luck. Okay, so I think, let's see, for paper 2, did we cover everything? I think we did, Euclidean and analytical. Euclidean, analytical, and trig. So we're not so bad. Grade 11 is actually not so bad. Grade 12 is actually more worse with them. They're more behind because there's more concepts in grade 12. So trig, Euclidean, analytical, please make sure to go revise the videos, go do practice questions. If you have any questions, please ask. But yeah. Okay, cool. Let's end it there. Thank you guys so much for joining once again. I will see you guys next week. Have a really